Okay, so good morning, everyone. Today we're going to continue our presentation of the influence lines. So again, I'm going to summarize what we learned last time, so that you don't, you can study. What's an influence line? There's nothing called influence line and full stop. No. Influence line has to be for a function. Okay, I cannot say influence line. Draw the influence line. No. Draw the influence line for AY. Draw the influence line for BY. Draw the influence line for the shear at point C, for example, for the moment at the point. Okay, those are the only 4 influence lines that you can have for a reaction. Or actually 3 influence lines. Influence line for a reaction. Influence line for a shear at a point. Okay, whatever that point is. Okay, it can be anywhere. And the influence line for a moment at a point. Those are the influence lines that you're looking for, okay? And we started doing this. What's an influence line? So it's the influence line for a function is the value, it's a figure that represents the value of that function when a unit load, a unit vertical load, is moving along that structure, okay? So we started doing this for this simple beam. So we had a simple beam like this, and then we started drawing the influence line for AY. So we put one unit load at a distance x from the support A here, okay? And we wrote the equation of AY as a function of the distance x, which is 1 minus x over L. So when you plot this function, it gives you here the magnitude of AY as a function of the location x of the distance of the unit. So you have a unit load at the distance x. So the variable is the location of that unit load, okay? And it looks like this. And then we did the same. This is the equation for By as a function of the distance x for that unit load 1 pound here. And this is the influence line of By. And then for the shear and the bending moment, now at the point C, we have some, an extra level of complication here, which is, it's not just one single equation that represents the shear at C, okay? You're going to have 2 equations. One if the load is on the left of point C, and one when the load is on the right of C, okay? So plotting those 2 equations, it comes like this, okay? One is just equal to AY, which is this one, this part over here, and one that is equal to BY, negative BY, which is this part over here when the load is on the left of point C. And the same for the moment. You have 2 equations when the moment is on the left and when the moment is on the right, okay? And you plot them, and it's always going to be like this. They intersect at point C, the point where you're calculating the moment at, okay? And it's AB divided by L. It's always like this, okay? Now, let's extend this to the influence lines in overhanging beams. So now we have an overhanging beam that looks like this. We just kept the distances, A, B, L1, and L2 to be, genetic. Just anything, or anything that we're going to learn here can be applied to any overhanging beam with any dimensions. So now, what's the difference between an overhanging beam and a single beam? It's just this extension, right? You can have an extension on both sides, just the left side or the right side, okay? So would that make any difference? Let's see. So let's start with the influence line for AY. How did we do this previously, okay? When we had the simple beam, the influence line is just the figure that represents the value of AY when a unit load, so let's put a unit load, 1 pound, is moving along the beam. So let's make this distance here, x, from point A. Now, what's the influence line of AY? It's the magnitude of AY. How much is AY in this case? So to calculate AY, let's take the summation of the moments about point B. You will find that AY is equal to 1 minus x over L. X is measured from point A, okay? So when you compare this equation, okay, to the equation that we had previously here for the simple beam, the same, 1 minus x over L. And x is measured from the support A, okay? The only thing that we have here, that this function, okay? So let's draw it now. Let's draw this function. The influence line of AY, it's 1 minus x bar over L, so we did this before. It looked 1 here and 0 here, so this is 1. But now the influence line is extending over the overhanging parts, okay? It's the same equation, it's just a linear equation, 1 minus x over L. So it's the same line, you just have to extend it and extend it from here. Okay? So someone would say, what if the unit load is over here? Would the same equation hold? Yes. You're going to take moment about point B, and you're going to have AY equal to 1 minus x over L, but x is going to be negative in sign. That's all. Okay? So it's the same equation wherever the load is. Okay? It's the same equation. It's not going to make any difference. So the influence line looks the same in the overhanging beam and the symbol beam, with the exception that it's extended over the overhanging parts. Okay? So that means one thing here, two important things. How much is the magnitude over here at the end of the beam? It's not 1. 1 is at the support A. Okay? When the load is at point A, the AY is equal to 1. Okay? All the load, all the unit load goes to the support A. But if it's over the overhanging load part, this unit load, okay? As you see here, AY is going to be larger than 1. Okay? So how much is this from the similarity of the triangle from those distances is going to be 1 plus L1 over L. Right? From those distances over here. Just the similarity of the triangle. Because this distance here is L, and this distance here is L1. Okay? And now, when the load is over here, somewhere over here, what does the influence line say? It means that it says that AY is negative. What does negative means? It's downwards. Okay? So that makes sense. If you have a unit load over here, then it's pulling AY upwards, so AY is pulling the support downward to keep it in equilibrium. And how much is the magnitude here? The maximum magnitude from it's the same straight line. Okay, so you can find it from the similarity of the triangles. That's going to be L2 divided by L. Because this distance here is L2. So what did we learn over here? The influence line in an overhanging beam is the same like the influence line over a single beam, just extending it over any overhanging part, whether it's on one side only, which is this side, or both sides. So let's say you have an overhanging beam that looks just like this, without this part. The influence line will look like this without this extension. Okay. You just extend it over the overhanging part that is in the problem. Okay? Any question? So let's continue then. Okay? So now the influence line of By. So now I'm not going to write the equation. Now we have a very simple rule. If you know the influence line of By over the single beam, just extend it over the overhanging parts. So here, the single beam, those are the supports here. Those two crosses represent the support, okay? So for By, it looked like this. 0 here and 1 here. So what would I do with those, overhanging parts? Just extend your line over those overhanging parts. That means that this is going to be 1 plus L2 divided by L. And this one part here is going to be negative. So it's L1 divided by L. And this is positive over here. That's it. Let's move to the influence line for the shear. So here, let me just write this relation that we find. So just extend the influence line in the simple beam over the overhanging parts. Now let's draw the influence line for the shear at point C. How would it look for a simple beam? So those are the supports. Let's say those are the supports. Those points represent the supports, the crosses. How did it look like? It looked like this. And what are those heights from last time? We said this is going to be, if this is A, then this is B over L, and this is A over L. This is how the influence line look for a simple beam. But what would I do with the overhanging parts? Just extend it, okay? So I'm just going to extend this line and extend this line here. So that's going to be negative and that's going to be positive over here, okay? And definitely you can find those heights, okay? If you have numbers, the numbers given, you can find them by, extension, okay? Those are going to be actually, let me see here, L2 over L, and this is going to be L1 over L, okay? So that's the influence line for the shear, okay, at point C. So as you see, the shear changes when you have a unit load, okay, applied over your beam, small beam, okay. If the unit load is here, the shear is negative at point C, okay. Sorry, the shear is positive, and then it decreases, and now if the load is here, the shear is 0, and then when the load moves here, the shear is negative at point C. All of those are the shear at point C. And then when the load moves here, the shear is positive, and then again turns negative. Okay? So the location of the load, okay, determines how much is the shear, okay? And then let's move ahead, okay? So that's the influence line of VC. And then how would I draw the influence line for MC? Again, just look for the simple part between the supports. Those are the supports. How does the influence line look like? We said at point C, you're going to have AB divided by L. And this is how it looks like. This is still valid. This is correct. Okay? But what would I do with the overhanging parts? Just extend them. Extend your influence line over the overhanging parts. Okay? So this is going to be A L2 divided by L, and this is going to be B L1 divided by L. And here it's negative, and here it's negative as well. So that's the influence line for MC. Okay? Any question? Okay, now let's go to a very important point. Can you use the influence lines to calculate those functions, AY, BY, the shear at the point, the moment at the point, okay? You're given a set of loads, okay? You're required to find, okay, the magnitude of those reactions or shear at the point or a moment at the point, okay? You know how to do this from the equations of equilibrium, okay? Or by taking a section, okay, at the point and finding the shear and the moment at that point. But actually you can calculate, okay, those internal forces using the influence line of that function. So how can we do this? So this is what we want to learn now. How to use the influence lines, okay, to find the magnitude of a certain function. This function can be a reaction or shear at a point or moment at a point. Okay? So let's say an example here. Okay? How we will do this? It all comes from the definition of the influence line. Okay? There is no theory, okay, or a new theory that we're going to represent here. Let's say you have a beam that looks like this. Okay? This is, by the way, it's an indeterminate beam. Okay? And you have point C over here. Okay? And let's say we want to draw the influence line for MC. The influence line of the function MC. That would look something like this. Okay? It will look exactly like this. Okay? So that's the influence line of MC. This is how it looks like. What does this influence line drawing mean? What does this height represent? What does this height that I just proved represent? What does this represent? It's a function, right? X is the distance and y is the influence line. What does this vertical distance mean at any point? Come on. If you don't answer this, then you don't understand what's an influence line. The only thing that you have to understand for an influence line is its definition. That's all. You're not getting the definition. What does this height represent? The value of the moment. At what point? About point C. Okay? For what?
For that distance.
No, for a unit load at that point. Okay? That's the definition of the influence line. That height represents MC, okay, when a unit load is standing at that point. That's the definition of that height. What does this height represent? MC, okay, again, because it's the influence line of MC. When a unit load, it's again, unit load, but now the unit load is at this point. That's what this height represents, okay? So any height here represents MC when a unit load is standing at that point, okay? So now, let's say you have a problem, okay, where we have 1 pound over here. Can you tell me how much, and this height, let's say this is H1. So now, let's say, okay, a unit point load, okay? Let's call this point 1, okay? And this point over here, 2. So we have, let's say, a unit load, point load, is applied at point 1. So I know MC is equal to H1. That's it, okay? That's from the definition. But we want, what if our beam, the load that is standing at point 1 is not 1 pound. Okay? So let's say now a point load of magnitude B1 is applied at point 1. Can you still use the influence line to find how much is MC? How much is MC? Would you know how much is MC? If there was just 1 pound here, MC was H1. Now it's not 1 pound. It's P1. So how much would MC be? P1 times H1. Okay? So I can still use the influence line for any load, even if it's not a unit load. Just multiply the ordinate by the magnitude of the load. Okay? But what if I have a set of loads, not just one load? Let's say now I have a load here, P2, in addition to P1. Can I still use the influence line to find how much is MC? Yes, superposition. Add them together. The effect of P1 is P1H1. The effect of P2, that's why it's called the influence line. The influence of P2 is P2 times H2. You have both applied together, then add the influence together. Okay? For a set of loads B1 and B2, MC is equal to P1 H1 plus P2 H2. What if you have 3 forces, 4 forces, 5 forces? MC is just the magnitude of BI times HI. Okay? HI is the ordinate of the influence line of MC, okay, at the point where the load PI is applied. So you can use the influence lines, okay? If you have the influence line drawn, you can use that influence line to find that function, okay, for which that influence line is drawn for any set of loads, okay? But that's when you have a concentrated force. What if you have a uniform load? Can you still use the influence line? What do you think? What about uniform loads? Can you still use it? What do you think? Who thinks you can use the influence line if you have a uniform load? Okay. It should not, logically, it has nothing to do with the definition of the influence line. The influence line is where you have a unit vertical point load, right? So we extended it, instead of just one unit load, we made that unit load any value, just multiply by the magnitude of that load. And if you have a set of loads, just add them together, right? But the influence line, the definition of the influence line has nothing to do with the uniform load. If you have a uniform load, then by definition of the influence line, it cannot be applied, right? So let's see if we would be able to apply it or not. That we want to apply it, okay? So now, let's say it's the same beam that we have, okay? It looked like this, okay? And let's say we have some uniform load applied on this location, okay? Or at any location. And the magnitude of the inflow of the uniform load is W. Okay? Okay? Now the influence line, this is, let's draw the influence line of MC. Okay? To use the influence line, the definition of the influence line, you need to have a concentrated force. Okay? So this uniform load, I cannot deal with it. Okay? I need to have a concentrated force. So someone would say, okay, just concentrate it. No, you cannot concentrate it, okay? Because if you concentrate it with a force over here, W times this distance L, okay? You're just assuming that, a unit load was here, okay? Actually, this is not correct because you had some load here, and the influence when you have a load here is so small, while when the influence when you had a load here is so large. Just finding the magnitude of this all load and putting it right in the middle, you assume that all the effect of this load at every location is equal to its effect when it's here, which is not correct. Did everyone get this point? Okay? So you cannot do this. You cannot concentrate the entire load and just put it right in the middle and that's it. No. So how would we tackle this problem? We want to have a small load, okay, where the influence line doesn't change. The magnitude of the influence line doesn't change. So instead of concentrating this as a whole, okay, I will just take a small piece, a very, very small part of the load, so that the influence line doesn't change within, the magnitude of the influence line doesn't change within that height, okay? So I will take this distance, okay, to be very small. What is a very small distance in math, differential calculus? Dx. Dx is the smallest distance ever. It's 0, right? That's dx. It's a distance that is almost 0, okay? So a very, 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 very small distance dx. So now I will just concentrate this force here. How much is the magnitude of the load in this very, very small distance? W multiplied by dx. Now, the MC due to this small load is just the magnitude here of W dx multiplied by this height, the influence line at this point. If this is x, the distance x here. Okay, measured from some reference points. So now, MC for this very, very small part of the load is what? It's the influence line multiplied by the load, W dx. This is the MC due to a very, very small load over this dx. This is MC due to small load of distance dx, okay, or of length dx at a distance x. But now you have to divide all this load into small parts and then add them together. What's the addition for those very, very, very small parts in calculus? Addition in calculus becomes what? Integration, okay? So actually MC would be, the summation of all the small parts, which turns to be the integration of the influence line of W dx. Okay? So now, doing this integration, W is the magnitude of the uniform load, which is constant. So you can move this out of the integral, because W is constant. For a uniform load, W is constant. Let me write this. For a uniform load, W is constant. It doesn't change from one point to another. It's a constant load, okay? Uniform load. So I can move it outside the integral here. So it's the integration of the influence line dx. What's the integration of a function? Okay, you have a function rho. What does the integration represent? It's the area under the curve. Okay? So this is W multiplied by the area of the influence line, okay, over which the load is applied. That is a very, very important rule. This is how you use the influence line to find the function if you have a uniform load. Just multiply the magnitude of this uniform load W, okay, times the area of the influence line over which that W is applied. You would get MC, or the value of the function that you're looking for, okay, for that given load. Okay? Any question? This rule applies for everything, okay? When you have a uniform load for any function, just W multiplied by the area of the influence line for that function over which this W is applied, okay? So let's see an example over here. Very, very nice example. So in this example, we have a beam that looks like this, a very simple beam, actually, okay? And this is point A, B, and C, and those distances are given, 2.5 feet and 7.5 feet. Okay? And we're required to find the maximum positive shear at point C due to a concentrated moving load of 4,000 pounds and a moving uniform load of 2,000 pounds per foot. In the problem, when I drew the beam, I didn't give you any load. Okay? I didn't draw any loads on it. What are the loads that we have? We have a concentrated force, okay, of 4,000 pounds. But where is it applied? It's not given in the problem. It's your task to know where is this 4,000 pounds applied. Okay? To maximize the shear, to maximize the positive shear. And there is also a uniform load. Okay? But where is this uniform load applied? It's not given. It's your task to find where is this uniform load would be applied to maximize the positive shear at point C. Okay? So you're given the loads, but you're not given their locations, okay? So you have to find their locations to maximize VC, the shear at point C. So how would I know which location for those loads maximize VC? The only answer that you have is the influence line. The influence line is the only thing that would tell you, okay, where to have your load where this VC is maximized. So you have to draw the influence line. I have to draw the influence line for what? For VC, okay? Definitely the influence line for MC is not going to help here. I want to know what maximizes VC, okay? So I need to draw the influence line for VC, okay? So that's the first step. Draw the influence line for VC. We learned how to do this before, so let me draw the influence line for VC. It's a simple beam, so going back to what we did last lecture, the influence line for VC would look like this, and this height over here is 0.75 because it's 7.5 divided by the total length of the beam, which is 10, and this one is 0.25. The units are pound because it represents the shear, and the shear, the units of the shear is in pounds, okay? Pounds or kips, no problem. So that's how the influence line of VC looks like. Would that help us know where to put the loads? What does this again, over and over again? What does this figure represent? What does each height here represent? It represents the magnitude of VC when a unit load is moving along the beam. Okay? If the unit load is over here, how much is VC? Negative something. Right? Actually, you want to put your load where VC is the maximum positive magnitude. So where would you put it? Definitely you want to put it here. I will put it here. Where exactly?
Just right.
If I put it here, it will give a VC of that height. If I put it here, it will give a larger bearing. So the maximum is over here.
Just right.
So I just put my load over here. But it's not a unit load, it's a 4,000 pounds. That's it for the 4,000 pounds at that point. Okay? That's the influence line. The influence line helps you to know where to put your load, okay? So now, the location, okay, for the concentrated force we're going to apply applied at the maximum positive coordinate of the influence line. Okay? Okay, what about the other load that we have? We have a uniform load, okay? The uniform load, we know the magnitude of it. The uniform load has a length. How much is the length of that uniform load? It's not given. Okay? Where would you put it? Okay? If I put my uniform load over here, it will give a negative shear. Okay? If I put it over here, it will give positive shear. So I just put my uniform load over here. What if I put the uniform load over the entire beam? It has a positive effect here and a negative effect here. So actually putting it over the entire beam is not, going to give the maximum positive, because actually this part is going to subtract some of the positive shear. So to have the maximum positive shear, just put the uniform load over the positive area. Okay? So put or apply it on the positive area of the influence line. So now we know the first answer, okay, for this question. We were given the loads, we were required to find the maximum positive shear due to those loads. The first thing that we didn't know, where are the loads, okay? So now I know where are the loads that would give me the maximum positive shear at point C. This is point C. Here you have the 4,000 pounds. This is the point, the location of the point load that maximizes the shear. And the uniform load is just going to be applied over here. Uniform load of 2,000 pounds per foot. So now that's the loading that will give you the maximum positive shear at point C. Now you just need to calculate VC. Third step, calculate VC for the given loading, or the, for the given loading. How would you find the shear at point C? You have two options, and on the test you're free to use whatever you want, okay? The first thing is using the method of sections. You have a beam with that loading, you want to find VC, take a section at point C, okay, and find VC. Or draw the shear force diagram and find how much is VC. You already know that's the loading, find the shear at that point, okay? Or you can use the influence line that you drew to find how much is VC. How can I use the influence line to find VC without finding the reactions, without taking the section? Yes. You have those two loads applied, and I want to find how much is VC. If you have a load, you remember here? If you have a concentrated force, okay? The value of the function is the magnitude of the load times the height of the influence line. If you have a uniform load, okay, it's W, the magnitude of the uniform load, multiplied by the area of the influence line over which the load is applied. So what do we have here? VC, we have both. We have a concentrated force. How much is the concentrated force? It's 4,000 pounds. Okay? I should multiply this 4,000 pounds by the height of the influence line over which it is applied. How much is this height? 0.75. Plus, if you have a uniform load, you multiply W, which is 2,000 pounds per foot, times the area of the influence line over which it is applied. Where's the uniform load applied? Just to the left of C, to the right of C. So you have to multiply it by the area of the influence line over which it is applied, by this area. How much is this area? It's a triangular area. So the area is just 1/2 the base, which is 7.5 feet, times the height, which was 0.75 pounds. Just add them together. VC is 86.25 pounds. What's this? That's VC maximum positive. Any question? Okay, great. Let's see another example here. On using the influence lines. So we have here a beam that is used to support a crane, okay? This point is A. It's, as you see here, it's an overhanging beam, okay? A, B, C, D. Those distances is 1.5 meters, 1.5 meters, 1.5 meters. This beam is to support the crane, so there is a crane, okay? There is a load here, okay? That crane, the crane can move, you know, anywhere, okay? The crane, the load of the crane here, and the crane can move along the length of that beam, okay? So we have this beam, and so here, for the problem statement, for the shown crane, with a moving load of 3 kilonewton. So that the load of the crane is 3 kilonewton, but it can be anywhere, okay? The load can move along the length of the beam, okay? We're required to find AY, the reaction AY maximum. How much is the maximum reaction at point A, okay, that can happen? And BY maximum, the maximum BY that can happen due to this load. And MD maximum positive, the maximum positive moment that can happen at point D, okay? If the own weight of the beam is 24 kilograms per meter. What's this? Now, we have three things to find: AY maximum, BY max, and MD max. Okay? So I have to draw the influence line for each one of those. Okay? So the solution, because the location of the load that would cause AY to be maximized might be different from the location of the load that makes BY maximized, and different from the location of the load that makes MD maximized. Okay? It doesn't necessarily mean it's at the same point. Okay? So the solution here, the first step, let's draw the influence line for any function that we want to maximize. Draw the influence lines. So I have to draw the influence line for AY, and the influence line for BY, and the influence line for MD. I use the influence line for AY to find the location of the load that maximizes AY, and then I use the influence line of BY to find the location of the load that maximizes BY, and then the influence line of MD to find the location of the load that maximizes MD. Okay? So let's draw the three influence lines. How to draw the influence line for AY? We already did this before, okay? So you can revise previous lecture or even today's lecture, okay? We have an overhanging beam, so how to draw it? Just draw 1 at the support. If a simple beam, just 1 kilonewton over here, 1 unit load, and it's 0 over here. That's for the simple beam, but actually we have an overhanging beam, so what would I do? Just extend this here, over the overhanging part. So that's point A, that's point C. If this is 1, if this height is 1, how much is this height? You go from 0 to 1 over a length of 3. Now this is 1.5. So that's 1.5 kilonewtons. Okay? This is how the influence line looks like. It's positive. You can put the hatching or for influence line, if you don't put the hatching, no problem at all. Okay? And then what about the influence line for BY? It's 1 over here and 0 at the other support A here. This is what you have for a simple beam. But an overhanging beam, you have an overhanging part, so you just extend this here. So how it's negative here, it's positive here. Okay? How much is this height from the similarity of the triangles? It's 0.5 kilonewtons. This is how the influence line of BY looks like. What about the influence line for MD? This is the support A, this is the support B. Point D over here is just right in the middle. The influence line for a simple beam for MD is just one height over here. It's AB divided by L. A is 1.5 meters, B is 1.5 meters divided by L, which is 3. So that is equal to 0.75 kilonewtons meter. And then you connect it by 0 here, you connect it by 0 here. That's for a simple beam. What should I do for the overhanging part? Just extend it. So how much is this height? This is 1.5 meters, and this is 1.5 meters. So it's 0.75. Okay? 0.75 kilonewtons meter. It's negative here and positive here. So I have now drawn the influence line for the three functions that I want to maximize, right? So now I have a unit load, or not a unit load. I have a concentrated force, okay? The weight or the load on that plate is 3 kilonewtons. Where would I put this 3 kilonewtons so AY is maximized?
If you had a support on the end,
The support is at point
I know,
A.
I'm saying if you did, had a support at C, would it have like a parabola shape in the moment?
So you have B, you have a support at B and A and C.
Yeah, correct.
If you have 3 supports like this, it's going to be an indeterminate beam. Okay? And at this moment, we didn't learn how to calculate the influence line for an indeterminate beam. Okay? Hopefully, if we have time today, we're going to learn it. If not, then we're not going to learn it this semester. Okay? Because it's not the scope anyway. So now, where would you put the concentrated force so that AY is maximized? Just look at the influence line of AY. What does this influence line for AY represent? Any height here represents the AY, the magnitude of AY, due to a unit load. So where would, what's the highest magnitude of AY? Here. If you put the unit load here, AY is maximized. It's 1.5 kilonewtons. So this is actually the location to maximize AY. So now, for AY maximum, the unit load would be applied at point C. Okay? So now, how much would AY maximum be? You have a concentrated force, right? If you have a concentrated force, if you use the influence line to find the magnitude of any function, just multiply the magnitude of the force, which is 3 kilonewtons, by the height of the influence line at the point where the load is applied. And the height here is 1.5. I want to apply it at point C. The height at point C is 1.5. So the load is 3 kilonewtons times the height, which is 1.5. Okay? It was 1.5. Okay. It's supposed, here the units, okay, it's 3 times 1.5 kilonewtons meter. So it's 4.5 kilonewtons meter, right? Don't write this. Okay? Why? Why did I ask you not to write it? Because it's wrong. Why? Why would that be wrong?
Because that's all.
There is another load that we didn't take into account here. What was that? The load of the weight of the beam. It says the weight of the beam itself, okay, is 24 kilograms per meter, okay? Where is that load applied? Why over the whole beam? Yeah, not because it's all positive over here. No, because this is a dead load. Okay, this is the weight of the beam. It's not a moving load. You cannot avoid it. You cannot say, okay, the weight of the beam is over here, but it's not here. You have a beam here, and you have a part of the beam here. Okay, you cannot say the dead load is just in this place and not in that place. Okay, the dead load, the own weight of the beam is everywhere. Okay, you cannot avoid it. Okay, so you have to add the effect of the dead load. Okay, the own weight of the beam. The own weight of the beam is a uniform load. Okay, this is the dead load. It's applied over the entire beam, and you cannot avoid it. You cannot play with this and say, okay, I'm going to apply it in this location, not apply it in that location. You cannot play with it. Okay, you can play with the live load, but not the dead. How much is that load? Okay, here we have the units in kilonewtons. The weight of the beam is 24 kilograms per meter. I want to change this from mass to weight. Okay, so I just multiply by the gravity acceleration, which is 9.81 meter per second square. Okay, so now we have a uniform load applied over the entire beam. I want to find AY as well due to this uniform load. How can you do this? If you already have the influence line drawn, just multiply the magnitude of the uniform load, W, by the area of that influence line. Right? By the area over which it's applied. So this is, I have to add the effect of the dead load, which is 24 kilograms per meter times 9.81 meter per second, okay, multiplied by the area of the influence line, which is 1/2, and then the length of the beam is 4.5 meters, and the height here is 1.5, okay? And this is going to be in newtons, so I just divide by 1,000, okay, Newton per kilonewton. Okay? So here we're going to have AY max being 5.294 kilonewtons. That's the maximum AY. And then for BY max, the maximum BY, where would you put the unit load so that BY is maximized? Where? Just raise your voice. Where? Here, point B. That's the maximum height. So that's the point where if the load is applied, BY is maximized. So the unit load, or the load, the concentrated load, is at point B. And therefore, BY max is the magnitude of the load, which is 3 kilonewtons, times the height, okay, which is 1 kilonewton meter, plus the effect of the live load, the dead load, which is the magnitude of the dead load multiplied by the area of the influence line. How much is the area of the influence line here for By? The area here is different from the area here. It's a different influence line. How much is that area? You have a positive area and negative area, so you have to sum them together. How much is the positive area? It's 1/2, 1 times 3. The negative area is 1/2, half times 1.5. Okay? So let's write the two areas here. The positive area is 1/2. The length is 4.5 times 1. And then the negative area, it's negative. Negative 1/2 0.5 times 1.5 meters. So By max would be equal to 3.264 kilonewtons. Why is it less than Ay max? For two reasons. If the load is here, it gives 1.5 kilonewtons. If the load is here, it gives 1 kilonewton. So that's one reason. The dead load all contributes to increasing Ay because the area here is positive. While the dead load here, when you have a dead load over here, it actually decreases By, not increases. And you cannot avoid it. There is a dead load over here. That's why By is less. Okay? Now, let's move to the third thing, which is MD. I want to maximize MD max here. MD maximum positive. Okay? Where would I put the load so that MD is maximized? At point D, because that's the maximum height over here. So I'm going to apply this load at point D. So when I apply the load at D, just find MD. I have two loads. I have the concentrated force, which is 3 kilonewtons, multiplied by the height of the influence line where this 3 kilonewtons is going to be applied. I'm applying it at point D. How much is the height over here? It's 0.75. Okay? So just multiply the magnitude of the load times the height of the influence line plus the effect of the uniform load. The uniform load, how much is the uniform load? It's 24 kilograms per meter times the gravity acceleration divided by 1000 to change it from Newton to kilonewtons, and then multiplied by the area of the influence line over which the load is applied. The load is applied over the entire beam because it's a dead load. Okay? So I have to find the area here, this influence line. Again, we have the positive area and the negative area. The positive area is a triangle. So the area of this triangle is just 1/2 the base, which is 3 times the height, which is 0.75. Let's write this. 1/2 the base times the height, which is 0.75. But we still have a negative area, which is triangular as well, so I have to subtract this negative area. Negative, and the area over here is 1/2, 0.75 times the base, which is 1.5. And that's it. MD maximum positive is equal to 2.38 kilonewtons meter. Any question?
Why did you put 4.5 instead
Thank you. Should be 30.
Oh, okay, yeah. So, thank you. Any question here? Okay, so that concludes this, question. Now let's move to a very, very nice method to draw the influence line. It's helpful to draw the influence line for any beam, but it's a qualitative method, okay? That means it will not give you the height of the influence line, okay? But it will give you the shape of the influence line. So you will not be able to use the influence line to find the internal forces or the reactions using the method that we found, but you're going to be able to use this influence line to find the location of the load that maximizes that function. You understand what I'm saying here? You have the shape of the influence line. Let's say here, the problem that we just solved. Let's say you have a way to know that this is the shape of the influence line. You can use it to know where's the location that maximizes your load, right? But you don't know how much is this coordinate and how much is this coordinate. So you cannot actually use it later on to find By, because you don't have the heights. Okay? So is there a way to draw the influence line to know the shape of the influence lines? Yes, there is a very, very nice method called Muller-Breslau principle. So qualitative influence lines. The method is called Muller-Breslau principle. What does Muller-Breslau principle say? It says that the shape, okay, that's what we're looking for, the shape. We don't care about the magnitude. The shape of the influence line for a function looks identical to the displaced shape of the structure if a virtual, it's not real, okay? If a virtual unit displacement, okay, in the direction of the function is applied. That's the principle that we're going to use. It's a very, very nice principle that helps you draw the influence line for any function. Let's see some examples on using this principle. Let's start with something that we already know, a simple beam. Okay? We have a beam that looks like this. That's a simple beam, and we have this length L. Okay? And let's say this point is C. Okay? Let's try to use this principle to draw the influence line for all the functions that we did earlier. AY, this is point A, B, and C. AY, BY, BC, MC. Okay? What does the Muller-Breslau principle say? It says that if you want to draw the influence line for a function, let's say AY, okay? Put a virtual unit displacement in the direction of that function. AY is a vertical, okay, vertical displacement at point A, okay, vertical unit load at point A, that's AY, okay, it's a vertical force at point A, it prevents the displacement of point A vertically, okay? So I'm just going to put a unit vertical displacement at point A, okay? And displace the beam. Let's say now you want to move this point 1 unit displacement vertically. How would the beam look like? Like this. Right? You still have this support. So the beam will just get inclined like this, right? So that's the Muller-Pressler principle, okay? It says if you want to find the influence line of AY, displace, this is the influence line of AY, displace the beam by a unit displacement in the direction of that function AY, okay? So that height is 1, okay? And see the displaced shape. Well, this is the displaced shape. This is how the influence line of AY looks like. There is no calculations. It's all imagination that you move the beam, the virtual unit displacement in the direction of the function. This is the displaced shape over here that represent the influence line. What about the influence line for BY? Just displace the beam, unit displacement, in the direction of BY, so it gets displaced like this. This is how the influence line of BY looks like. Now, let's take it one step further. The beam looks like this. There is a support here and support here. This is point C. I want to draw the influence line for VC. The influence line for VC. How would I do this? The shear. What does the shear look like at the point? You remember the shear? How to get the shear? You just need to break the beam at that point, and the shear looks like two loads like this, right? That's the shear, right? So I'm just going to take the beam here to be able to put the unit displacement, okay? The unit displacement. And then I'm going to move the unit displacement like this. I'm just going to move this down and this up. I'm just going to move this down. I'm just going to move this up. And this is the displaced shape, okay? So here, this is the displaced shape. So the displaced shape looks exactly like the influence line. This is how the shape of the influence line of that function looks like. What about MC? I want to draw the influence line of MC. Here, at point C, there is a moment. I want to release it so that I can put the unit displacement. So to release the moment, assume that there is an internal hinge here. And now I want to put a unit moment. Okay? Just put the unit displacement here, unit rotation. Just rotate the beam like this. Okay? How would the beam get displaced? That's the shape of the influence line. Okay? Anyone didn't get this Muller-Pressler principle, how to apply it? So simple. Just release the function, okay? Put the unit displacement in the direction of that function. See how the beam is going to be formed. The shape of the deformation is the shape of the influence line. Okay? Any question? Okay, great. Let's take more examples here on using the Muller-Pressler principle. Example 6.9. We're required to draw the influence line of AY for each of the shown beams. First, we have a cantilever beam. how to draw the influence line here using the Muller-Pressler principle. This is point A. Push it up in the direction of AY. Push the beam up. If I push it up over here, is there a support here that, prevent the beam from moving up? No, so the entire beam would actually move up. So the influence line, pushing this up, the entire beam will move up. That's the influence line of AY. It's 1. Wherever the load is, AY is the same, doesn't change, because the summation of the forces in the y direction is equal to 0. If you have the unit load at any location, AY is remaining, it's going to remain as 1. Okay? Let's see here. An overhanging beam like this, and this is point A. I want to draw the influence line. How would I do this? Displace point A vertically in the direction of AY. Okay? So point A moves here. But at this point, there is still a support, so it's going to move like this. Okay? And it's a rigid beam. So straight line would remain straight line. The beam is still straight, right? So that's the displaced shape. And now this displaced shape looks the same like the influence line. And this magnitude here is 1. Okay? Let's see here. We have this compound beam, okay? And this is point A. This is the last thing that we're going to do here. I want to draw the influence line for AY, okay? How can I do this? Just push the beam up here, okay? So pushing this up, okay? There's still support here, so I'm pushing this up a unit displacement. So this is going to remain straight like this, but the beam here is not broken. Okay, I just move this up. So it's going to move up all the way right to the hinge. And then the hinge is the point where it can rotate at. And then you have a support here, so it's going to just move like this. You agree with this displaced shape? Anyone disagreeing? That displaced shape is the shape of the influence line for AY. And it's 1 here. Thank you a lot. Any questions? By the way, I finished grading the test, okay? And you can stop by my office to see your paper and how much you got, okay?
Okay. So one of the new medicines that the neurologist had put made my blood pressure get really high, and that's what made me useful. So we got that kind of figured out.
You're good now.
Yeah, I'm making it. This is the homework. I was gonna email it to you, but it's like 12 pages. So thank you.
Our report, the written part, do you want it bound?
Stapled is
Staples, okay. All right. Thank you.
project, do we do the equations that have the earthquake load in them?